All right, we're going to start here by looking at some of the rules. Now, I kind of highlighted and bolded the important parts, although you can refer to them, as needed. First things first, count the total number of valence electrons or dots that you need to represent in the structure. So you need to look at each atom, how many of each atom or element, and decide how many valence electrons it brings to the bonding party, basically. To represent this, we're sharing electrons because these are covalent compounds. Even the polyatomic ions, yes, the polyatomic ions will do ionic bonding with something else, but within the polyatomic ion, the group is held together by covalent bonds or sharing electrons. That's why we also draw them and represent them as Lewis dot structures. So, for example here, I'm just going to start with the water. You guys know water. Water is very basic. It's on your sheet there, but let's go ahead, take a look at it. For rule number 1, here's water. I'm going to count the number of valence electrons represented by the atoms in this formula. So hydrogen has 1, but there are 2 of them, so that's 2 electrons, 2 valence electrons coming from hydrogen. Plus, the oxygen brings in 6, so that's a total of 8 that I get to work with. 8 dots, 8 valence electrons. So that's the first thing you need to do before you begin is count. And yes, you'll get better at it, so you won't actually have to write it down each time, but in the beginning, make sure you're writing down your counts and ticking them off as you go. It'll make it so much easier. Now, the second thing is we have to identify the central atom. Which one goes in the center? Now, of course, this applies to anything that has more than 2 atoms. Anything with just 2 atoms, you're just going to attach together, right? Does that make sense? Because there isn't really a central atom if you only have 2 things that go together. But if you have 3 things, then that means one has to be in the middle. So, usually is the first atom in the formula, but it can never be hydrogen. Hydrogen can form one single bond with a maximum of 2 valence electrons. Remember, hydrogen likes to mimic helium, so it's only going to need 1 bond to share and to get a maximum of 2 valence electrons. So hydrogen will never ever be in the center. The other criteria that we look at is electronegativity. Does everybody remember that electronegativity trend? What's the trend of electronegativity? Up is going to what? Increase. To the right is going to increase. So we go up to the right, the electronegativity is going to increase. But usually the least electronegative element is the one that goes in the center. So here, with water, what is our only option that can go in the center? Oxygen, because hydrogen cannot. So we're going to put oxygen in the center. Now, the next rule, so far I've done this one. 3, draw single bonds to all the ligands. Now, ligand is a general term for the outside atoms, the atoms that you attach to the central atom. In this case, our ligands are going to be hydrogens. So, I'm going to attach the ligands with single bonds. Now, a single bond is represented by 2 electrons. And I use lines, you can use dots. But as shown in your diagram as well, this is showing you that's 2 electrons shared. It is called a bonded pair. Let me just try that again. It's called a bonded pair because it's between the 2 atoms. Being between the 2 atoms makes it a bonded pair. 2 electrons being shared. One line represents 2 electrons. You are also allowed to use 2 dots there if you'd like to, or you prefer the dots. So that is step 3. We've done that. Now, step 4 says, satisfy the octet rule for the ligands by adding lone pairs. Does the hydrogen need any more lone pairs? Hydrogen wants a maximum of 2. Each hydrogen already has 2, so hydrogen doesn't need any more. So what I've used so far, I've used up 4 because this is 2, this is 4. I have 4 left. that I must assign to the molecule. Now we need to count all of the electrons in the drawing. If you have all the dots you need, move on to step 6. If you have more electrons to add, do we have more electrons to add? Yes, we have more electrons to add. Add them to the central atom by adding lone pairs. And lone pairs are always the dotted pairs. So, there goes my 4 extra. I added them to the central atom. Now I'm down to 0, which is good. The next thing I need to do is look to see if everything is satisfied. Do the hydrogens have 2? Does the oxygen have 8? And when you're counting, you're looking here. This is 2, this is 2, 2, and 2. So, the hydrogens have 2, the oxygen has 8, everything is satisfied. You can move on from this Lewis dot structure. Now, we're going to look at some of the other rules real quick, and then we'll start doing the examples. Now, right here, number 6, does the central atom satisfy the octet rule? Does it have 8 dots? If yes, then you are done. If no, sometimes you run out of electrons and you don't have enough. If no is the answer and the central atom does not have 8 and you've already run out of electrons, you have to engage in using a double or triple bond. And basically all you have to do is remove a lone pair off of one of the ligands and create a double or a triple bond. And I'm going to show you how to do that. Now I gave you the examples here of what they look like. Double bonds have 4 electrons, so you can use 4 dots, as shown in this picture right here. Or you can use 2 lines where each line represents 2 electrons. So you can use 2 lines or 4 dots for a double bond. You can use 6 dots or 3 lines for a triple bond. Sometimes you'll have to triple it up to make it work because we have to satisfy the octets of all the atoms. Now we got to talk about some of the exceptions and rules along the way of certain atoms. This is where it gets difficult because you have to remember certain exceptions and certain facts. Like hydrogen always needs 2. Like that's important. You just have to know that. Hydrogen mimics helium. Carbon, nitrogen, oxygen, and fluorine, which are in energy level 2 or the second period of the table, they're always only going to have 8. They do not do more. They do not do less. They're always 8. This means they have 8 electrons no matter what. Some of the other ones are going to be able to do more. Some of the other ones you're going to see have less. So there's other exceptions here. General bonding, though, for our group 14, 15, and 16. Group 14, the carbon group. I'm talking about carbon, silicon, germanium. Because these are our nonmetals and our metalloids that will engage in covalent bonding. They're going to form 4 bonds. So you have these different options. For instance, carbon can do 4 single bonds. Carbon can do a double bond and 2 singles. Carbon can do 2 doubles. Carbon can do a triple and a single. So, but you notice in all of those arrangements, that is a total of 4 bonds around the carbon. Carbon does not do lone pairs typically. Okay? If we're talking about the nitrogen group, that's nitrogen, phosphorus, arsenic, antimony. The nitrogen group, they do 3 bonds. So you could have a lone pair and 3 singles. You can have a lone pair, a double, and a single. And you can have a lone pair and a triple. It's going to have 3 bonds and a lone pair typically. Unless it's in the expanded octet realm, which we're going to go over later. The oxygen group, and this always, it pretty much goes for oxygen, except for a few minor little crazy exceptions. Oxygen's always going to form 2 bonds. So oxygen, as shown in water, have the 2 bonds and the 2 lone pairs. Oxygen can also form a double bond with 1 thing, but a maximum of 2 bonds and 2 lone pairs. Usually for oxygen group, the sulfur, the selenium, the tellurium, So keep that in mind. Those are general trends of those groups, especially if we're not talking about expanded octet molecules. They're going to follow these normal trends. So the next thing that's important to realize too is there's a few weird exceptions. And I call boron the moron because boron does not follow the octet rule. Boron is satisfied with 6 valence electrons. So this is an exception. You just have to memorize 6 valence electrons for boron. So what you're going to see, boron's going to have 3 single bonds typically. The other one that's a little crazy here is beryllium. Beryllium's a metal. Why is beryllium engaging in covalent bonding when most metals do ionic bonding? Well, it does. It's just the way it is. It does some covalent bonding. But it only needs 4 valence electrons to be satisfied. So basically, you're going to see these linear molecules of beryllium with either the halogens or with hydrogen. When it typically have 2 ligands attached to it, and it's going to be satisfied with 4 valence electrons. It is strange. It is just an exception you have to know. Yes?
Can it do double bonding? Really?
No. It does 2 singles. All right. Last but not least, the halogens, when they are ligands, and fluorine always. Fluorine's only going to do a single bond, by the way. But chlorine, bromine, and iodine can do expanded octets. We'll see those later. But if they are an attached ligand around the central atom, they are only going to do a single bond, and they're going to have 3 lone pairs. So keep in mind that's how these halogens work. If they're around a central atom, now if they're like chlorine's in the center, or bromine or iodine are in the center, then you might see some expanded octets happening. So let's take a look at our first example here. Arsenic trichloride. And this is under the has all single bonds example. So we're going to go back and we're going to start practicing with our rules. So let's take a look. We have ASCl3. Rule number 1 says we're going to do what? Count valence electrons. Okay, so how many does arsenic bring to the party? 5. Good. How many does the chlorine bring to the party? 7. But there are 3 of them, so we have to multiply by 3. So this is the total of how many valence electrons? 26 we get to work with. 26 valence electrons. Always total in the beginning. You'll get better at it. You might not have to actually write it down each time, but what's rule number 2? Identify the central atom. So, do we have hydrogen up here? No, so we don't have to worry about that. Hydrogen doesn't go in the center anyways. Is arsenic less electronegative than chlorine?
Yes.
Yes. Is it the first atom? Yes. So typically that's what's going to happen. So we've identified our central atom as arsenic. What's the next step say to do? Draw single bonds to all the ligands. And our ligand here is what? Chlorine. So we're going to attach single bonds to our chlorine. Good. How many electrons did I use to form those single bonds? 6. So now how many do I have left? 20. I have 20 left. Good. What does the next rule say? Add the lone pairs to the ligands. We got to add them to the ligands first and satisfy their octets. Good. So let's add. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18. How many do I have left now? 2 left. So, what do I do with those 2 when I have electrons left over? Where do they go? Automatically to the central atom. So we're going to stick them on the central atom. Good. Now we need to double check and count. It says each of our chlorine have 8 electrons around it now. Yes. So make sure you count. Yes, so this is 2, 4, 6, 8. Good. Does the arsenic have 8 around it? 2, 4, 6, 8. Yes. So each chlorine is good. The arsenic is good. Everything's satisfied. You are done with this drawing. So now what I'd like you to do is try some of the practice ones on your worksheet for the single bonds. All right. Looking at ones that might have a double or a triple bond in here. So let's take a look at some of these examples. SiF2O. First things first, just like always, we count our dots. So how many does silicon bring to the party? 4. How many does the fluorines bring? 7 times 2, yes, is 14. And then how much for the oxygen? 6. So 14 plus 6 plus 4 gives us 24. Good. We have 24 to start with. Which one is the central atom? Silicon. It is the least electronegative and it is the one written first. So we're going to put silicon in the middle. Then we're going to attach our ligands. Doesn't really matter which side you do attach them to, just as long as you attach them. I happen to like to go clockwise, so that's what I'm going to do. How many electrons did I use in order to attach the 2 fluorines and the 1 oxygen? 6. So now we're down to 18. What does the next rule say? We've got to satisfy the ligands or the outsides, the oxygen and the 2 fluorines. So let's do that. So that was how many? 18. Now we're down to 0. Okay, we have now no longer have any more electrons to contribute to the structure. But you should see a problem here. What is the problem? Silicon is not satisfied. Silicon only has 6. So this is a problem. So we are going to have to use the idea of making a double bond. Now, which one of our ligands has the ability to do a double bond? Oxygen, because remember, fluorine can only do a single bond with 3 lone pairs. So, what you do here is you take off a lone pair from the oxygen, erase it, and you contribute it to the bond between the silicon and the oxygen. So now, if you look here, there is a double bond between the silicon and the oxygen. And now silicon has a total of 8. And of course, we would pick the oxygen here because oxygen can do up to 2 bonds, 2 lone pairs, whereas the fluorine can only do a single bond with 3 lone pairs. So you have to know that rule in order to make sure you pick the correct ligand to take from. Okay? So that's one example where we have a double bond. Let's look at an example where we have a triple. CNBr. Let's count. So we have 4, we have 5, and we have 7. That is a total of 16. Which one goes in the center? Carbon, least electronegative. Now, carbon, when the carbon group has 2 things attached, I always draw it linear. I'm going to tell you later on why that is, but I'm going to draw my ligands that way. So I'm going to put the nitrogen here and the bromine here. When it's group 15 or 16 central atoms, I always draw them like clockwise. But if it's a group 14, I make it look linear because the shape is linear and it's easier to remember that if you can remember to draw. When carbon is in the center, silicon's in the center, you have 2 things attached. You want to draw it this way. Now, looking up here, we have used how many electrons? 4. So now we have 12 left, correct? Now we're going to satisfy the outside atoms. So I have just used all of them. Now we're down to 0 again. And if you look at carbon here, Carbon only has 4. So that is a problem. And once again, if you're looking at as a ligand, bromine being a halogen is going to have 1 single bond and 3 lone pairs. So which one can form more bonds? Nitrogen. So we're going to pull from nitrogen. We're going to take one from nitrogen here and make a double bond. Does that fix the problem? No, because here carbon only has 6. We have to do it again. So we're going to take the other one off down here and form the triple bond. So now carbon does have 8. Nitrogen has 8, the 3 bonds and the 1 lone pair. And the bromine has its 1 bond with the 3 lone pairs. So now go ahead and try some in that section. We'll come back in a few minutes. All right, the expanded octets. So they apply to these notes here. Now, principal energy level 3, which is period 3 on the table. Guess what? They all have those d orbitals and those higher energy levels. So they can pack in more electrons than 8. It is a possibility. So, anything period 3 that's typically going to be like phosphorus, sulfur, chlorine, arsenic, selenium, bromine, antimony, tellurium, iodine. Sometimes krypton and xenon will also engage, even though they're noble gases and they already have 8, they will form compounds with expanded octets as well. So if you're looking here, these are the groups that are usually the central atoms on these expanded octet ones. And if they are in the center, they follow totally different rules than before. They are going to have more than 8. They could have 10, they could have 12, some of them have 14, depending on extra lone pairs. So let's go ahead and take a look. They're going to exceed the octet rule. That's because they have those extra orbitals, so they have the ability to pack in more than needed. Let's look at this example, Iodine Pentafluoride. First step always is counting electrons. Let's do that. So we have 7 plus 7 times 5. That's going to be what? 42. Good.
I was going just
42. Okay. Now, obviously out of those, which one's the least electronegative element? Iodine. Fluorine, of course, can't be in the middle because we all know fluorine can only do 8 and can only have single bond with 3 lone pairs. So, we put I in the center. Now, this is how I draw these. I'm going to add my 5 fluorines to it. I always do 1 on each side first. And then it doesn't really matter which one you pick. You just put the other one off the diagonal. So I don't care which diagonal you pick, but stick it off the diagonal there. How many electrons did I use now? 10. So we have now how many? 32. And we have 5 ligands, 5 fluorines that all need 6 more, right? So 5 times 6 gives me 30. So let's use up those 30. So now I have 2 left over. What do you always do with extra electrons? You put them on the central atom as a lone pair. Doesn't matter which diagonal you stick them on there as, but stick them on the central atom as a lone pair. Now you're done. That particular iodine has 12 around it, right? 12 electrons. That is over 8. That means it's an expanded octet. All right, so go ahead and try a few of these. All right. Moving on to those lovely polyatomic ions. As said before, polyatomic ions are a group of atoms that pick up electrons if they're an anion. They lose electrons as a group if they are a cation, like ammonium. But either way, as the group is formed from covalent bonds, where they share electrons. So we can represent them by Lewis dot structures. So, the issue with the polyatomic ions is if it's an anion, the negative ones, these guys right here, you have to account for the charge. So if it gains electrons and has a negative charge in it, then you have to add that to the valence electron number. So for sulfate up here, since the sulfur has 6, the oxygen is 4 times 6, so that gives us 24, but because it has a -2 charge on it, we have to add in 2 extra electrons. For the positive ions, you would subtract from the number in the charge. So, for instance, here I'm showing you hydronium, H3O+, different than ammonium, because that's another cation version. You have 3 valence electrons for the hydrogen, 6 from the oxygen, but since you have the +1, you have to take away an electron, so now all you have is 8 available for the drawing. That's the only really added extra little glitch here for drawing polyatomics, although you might see some expanded octets in some of them. If I wanted to draw hydronium here, I would still follow the same rules. I have 8 electrons. I'm going to put my oxygen in the middle. I would attach the ligands like so. Okay, that's 6 electrons. So now I'm down to 2. I put my other pair on the oxygen like so. And this is the only other added tidbit for being an ion. You add brackets around it, like so, brackets, and the charge in the upper right corner. Okay? This should say right. Upper right corner. Upper right corner is where the charge goes, as you see in the diagram. So correct that. That should say upper right corner. So, keep in mind, it's the same rules. Add in the extra electrons, subtract the extra electrons, depending on if we're talking about an anion or a cation. Put the brackets around it and add the charge. So go ahead and take a moment to do 1 or 2 of those. All right, yes, let's take a look at the example here for sulfite, SO3 - 2. Let's do that example. 6, we have 6 times 3. Now we have the -2, so we have to add in 2 extra. So that's going to be 26, correct? Now, just like before, we put the S in the middle because it's the least electronegative. We attach the ligands. Okay, so now I'm down to 20. I satisfy the octets. That's 18. So now I'm down to 2. That extra pair goes on the sulfur. And all I need is brackets and the charge in the upper right corner. So that is how you would draw sulfite. Okay, looking at resonance structures. Resonance structures. When a single fluid structure cannot fully describe the bonding, there's a combination of possible resonance structures defined as a resonance hybrid. Represents the overall delocalization of electrons within the molecule. So basically, we're looking at this example of carbonate. We drew the first one. You would end up with this where one of the oxygens gets the double bond, the other 2 do not. Does everybody see that? Well, the oxygens are equal ligands around the central atom. They all have the same kind of pull on the central atom. So that extra pair that's in the double bond doesn't actually just go around one oxygen. It actually kind of splits itself and spends equal time around all 3 oxygens. So a resonance structure has to show how it is equally double bonded to all 3 oxygens. So you have to draw all 3 structures with the arrows between them, showing that this one is more of a blend, it's more of a hybrid. That's why we place the arrows between them, so we're saying like the double bond equally shared amongst all 3 of those oxygens. Now this is a representation of a polyatomic ion that has resonance. You can have other structures that are not ions that have resonance. But you have to draw all the possible structures showing the double bond switching from each ligand. So, let's take a look at the example that's in your notes sheet. I believe it's sulfur trioxide. This is similar to sulfite, except for we're missing 2 electrons. So 6 plus 6 times 3, so that gives us 24. We have 2 less electrons than the previous example. S still goes in the center. We're going to attach our ligands. Okay, that's now down to 18. But you notice, in this case, we run out of electrons. So I'm down to 0 now. So one of them has to double bond. So let's say this one, I decide to double bond up. This one forms a double bond. But I could have chosen either of the other 2 oxygens. So I still have to represent the other 2 structures. Draw the arrow between and show the other representations. So we have S here. We have the O. Sorry. This one I'm going to make the double bond this time. So that's one of the other structures. Then we have to draw the third one where the double bond is on the last oxygen. In this case, the double bond would be on that side. Now I have drawn the correct Lewis dot structure for sulfur trioxide, showing the double bond being equally shared amongst all 3 oxygens. Now this case is only going to happen if you have identical ligands where there is a double bond that needs to be shared. So that's only going to happen in those kind of cases where the ligands are all the same and the double bond has to be spread over all those identical ligands. Last but not least, I want to do the example where you might have a molecule that has more than one central atom. And you'll see them written like this, C2H6. Okay, there's more than one central atom here, and they're very frequent in those organic molecules that we're going to get to later on. You would still count up the electrons like normal. So this would be 4 times 2, which is 8. 6 times 1 is 6. So that's a total of 14 for this particular structure. In this case, though, we know what about hydrogen? Can never be in the middle. So we're going to take both carbons and stick them in the middle together. So you start off by putting them together in the center, like so. Since hydrogen can't be in the center in this case, too, you'll notice this about a lot of the hydrocarbon molecules. You have 6 hydrogens. So that's an even number. They're going to equally spread along both carbons. So I've used 2 electrons out of my 14. So now I have 12 left. I attach 3 hydrogens to this carbon. Guess what? That's 6. So now I have 6 left. I'm going to attach 3 to this carbon, these on the right, and that's my last 6. So this actually is a molecule of ethane. Okay? And if you count, there's 14 electrons. They're all single bonds. Now, mind you, I will warn you that some of these guys, where you have multiple central atoms, sometimes they have to form double and triple bonds between them in order to satisfy the octets as well. So you might see some blending in here. Double, triple bonds frequently appear in some of these that have more than one central atom.